sit down. Okay. Should I just go? Okay. All right. Hi. I'm Plamen Jeliazkov. Thank you all for coming here, especially if you've bumped into me along the way. I know some people were pretty excited to come here. So just thank you, first of all, for being here. I'd like to just give a quick thanks to my family and friends who are supporting me. Let's get on with the show. Okay. So yeah, I'm actually a fresh undergraduate from UCSD. I just got my BS in computer science, and I'll be pursuing a master's afterwards. I interned at eBay last summer under Konstantin, and I knew basically nothing about Hadoop at the time, and it's been a wild ride since then, and I've learned a lot under him. So I'd also like to just thank him and the people I worked with during my time at eBay. Yeah. And so most importantly, what we're going to be talking about is a new file system named Giraffa, and I implemented it. It's Konstantin's design. We just released the source code for it in Apache Extras, which Konstantin will go more into. And we won't have enough time in the presentation for a demo, but there is one. And if you come and find me afterwards, I would be glad to give you a private demo. And it'll be very technical, but yeah, just come and find me. Again, I'm Plamen Jeliazkov. Yeah. Okay. And with that, I'd actually like to give it to Konstantin, who will explain Giraffa in great detail. All right.
Yeah, thank you, Plamen. Konstantin is here. I'm a founder of Autoscale. The primary focus of the company is the Autoscale workbench, which is a way to run Hadoop and HBase cluster on the public or private clouds. And Giraffa, the topic of this talk. I'm a Hadoop PMC member, and I've been doing work on HDFS scalability for several years now. So the content, so we'll go over some background. I'll try to go faster on those slides because everybody knows the backgrounds of Hadoop already. If not, then you probably learned already on this conference. So I'll touch on the motivation and get into architecture, general architecture, and finally, I'll talk in more details about main problems and solutions for them that are related to distributed namespace. The three of them are bootstrapping, namespace partitioning, and atomic renames. So what's Giraffa? Giraffa is a distributed, highly available file system. It utilizes features of HDFS and HBase, and it's a new open source project in the experimental stage. It's in no way a production-ready system yet. The origins of Giraffa are here. In Latin, it's called Giraffa camelopardis. Okay, I learned that. In other languages, the name sounds similar. First, giraffes were called giraffas in Arabic, and it sounds like zarafa or something. Spanish, Bulgarian, and Italian have same pronunciations. As the traditional of Hadoop project requires, this is the animals, the giraffes are the favorites of my daughter. She's author of multiple, innumerous pictures of giraffes. This is one of them. And one word that don't mix it with another project called Giraffe or Giraffe. This is a graph processing framework. It's a good project, but it's a different one. So on the background, Apache Hadoop is a reliable, scalable, high-performance distributed computing system. The main components, the core components, is the distributed file system, which is a reliable storage layer. MapReduce runs on top of computation. It's a computational framework. It's a very simple computation. As you know, you just define two functions and you're done. You can process lots of data. Hadoop scales computation and storage capacity. So the design principle, four main design principles here, linear scalability. If you need to accelerate your computation, you just should be able to add more nodes and computation will run faster, or vice versa. If you have twice as much data as to process, you should be able to double your cluster and the task will run in the same time. Reliability and availability is important. A drive fails once in 3 years. That's a probability of 1 to 1,000 that your drive on your laptop will crash today, but on a cluster of 1,000 nodes, several drives die every day. And that should be in the design. Moving computation to data avoids transferring of large amounts of data, and sequential data processing avoids random reads. So this is a typical Hadoop cluster. As you see, there are two actually clusters collocated on every node has a component which belongs to MapReduce cluster, and another component called data node belongs to HDFS. That way, computes are executed locally to the data. So job tracker, name node, task tracker, and data node are the main servers that run on the cluster. So about the Hadoop distributed file system. The namespace is a hierarchy of files, as in normal file system. Files are split into large blocks. Typically, it's 128 megabytes, sometimes more. Namespace is decoupled from the data. This provides fast access to metadata and direct streaming to the local storage, data nodes in case of Hadoop. Single name node keeps the entire namespace in RAM. Data nodes store blocks, those 28 megabyte blocks, in local files. And blocks are replicated on 3 data nodes for both redundancy and availability. HDFS client is an entry point for HDFS. It communicates with name node for metadata, gets block locations, and then connects directly to data nodes to transfer data. So the scalability limits are well known right now. So it's the single master architecture, both on HDFS and MapReduce side. 100 million files and 200 million blocks. That's approximately the amount of objects you can put on a single name node with 64 gigabyte RAM. And this does not include the headroom, which is recommended from 50% to 100%, so that name node could run smoothly and not go into full GC. And that restricts the storage capacity if you calculate and take into account block to file ratio, which is here assumed as 1.5 blocks per file. Then you get a 20 petabyte file, and there are clusters that run at this scale at Yahoo and at eBay, for example. Facebook has bigger clusters. Important scalability limit is that performance is that linear performance growth. If we have seen cases when a name node could be saturated with a handful of clients. One example is you can run DFS.io with which that's a benchmark in Hadoop, which creates very small files, and you'll see that name node will get into bad stage. Another example was people were running a very small job, only 200 mappers, but the job was trying to access non-existing file in HDFS, and that basically stops the name node and doesn't let you do anything with it. And it's known that framework, MapReduce framework, reached its scalability at 40,000 clients. This corresponds to Yahoo's cluster of 4,000 nodes with 10 MapReduce slots. And I talk about, you can find more information on scalability in my login article. So what's happening right now? We see that the horizontal scaling is limited by the single master architecture. And right now, with natural growth of computers are getting better. They have more drives, more cores, and more CPU. And so the density of those computers is growing, and this provides vertical growth of the cluster. And in fact, the clusters are shrinking. So we see over years, the cylinders are the clusters. So the width of the cluster is the number of nodes on the cluster, and the vertical is the resources per node. It could be cores, you could local disk or measure RAM, and you see that the clusters are getting higher, but they're shrinking in size. And so we project that. Those are different snapshots from different times, and we project that in 2003, based on current orders, the clusters will shrink into 500 nodes, and that is not enterprise scale system anymore because the cost remains the same. So there is the future in Hadoop 2.0. It addresses some of the issues. This is Federation, which lets you run multiple namespaces. They represented for the user as single nodes. As single file systems, but they share the data nodes. So this represents the same a single cluster as a operational unit. And the new MapReduce framework also provides further scalability of the MapReduce framework. So talking about HDFS, namespace partitioning in Federation is what we call static partitioning. And that means that if one of the volumes grows faster than another one, there is no easy way to repartition or automatically repartition and move data on the less busy nodes or having less data. So in dynamic partitioning, it's done automatically, and that's what we want to achieve with Giraffa. The approaches are orthogonal in general, and you can federate, for example, traditional HDFS and dynamically partitioned file system into one federated namespace. So it's all interchangeable. There are known solutions already that implement dynamic namespaces. Ceph was one of the first one. Luster is still working on it. Colossus from Google, and we learned about it from Quinlan and Jeff Dean publications. Uses Bigtable and GFS, similar ideas. Oh, our ideas are similar, of course. to build a bigger file system. There are prototypes that are based on Voldemort and Cassandra as the namespace service. And also recently, last summer probably, HDFS uses MySQL to store namespace. Those are prototypes. I'm mentioning them. So a little bit of HBase overview. It's a big, sparse, loosely structured table. It's a collection of rows. Rows are sorted and identified by row keys. You can have arbitrary number of columns in different rows. For us, it's important that table is split horizontally into regions. And regions provide partitioning, dynamic partitioning of the namespace. Regions are served from region servers, and if a region server dies, they will be reassigned to other servers, and that's what provides dynamic partitioning. Columns grouped into column families. This is a vertical splitting of the tables. And important also that HBase can be considered as a distributed cache for real-time access of data. The API is split basically has three main is very simple in HBase. And it has three main components. So first is an administration API that lets you manipulate tables themselves and columns. And there's some administration function for splitting, compacting. Then there is an HTable API, which provides you access to the table itself. You can query particular rows, update them, or create, remove. You can have scans. There is lots of good features like filters. And there is a free API for creating anything you want, basically, and to run on the servers, which is recently introduced to HBase, called co-processors, and we took advantage of that to build Giraffa. This is the known picture of HBase architecture. I think somebody from HBase community draw it. So for us, it's important that HBase, there are two region servers here. If you can see, they rely on the HDFS layer to store tables in H files. And it's important for us to store those files. It will be important to store those files in Giraffa. So our main goal is to build the file system from existing building blocks. We want to use HDFS data nodes as the storage for blocks, but we also want decoupled namespace, which is highly available, and we'll use HBase tables to store that metadata. And the third component is the block management. Because HBase relies, as we saw on the previous slide, on HDFS, we need the block management, which will not only maintain blocks, but also provide that storage for HTables. The requirements are simple. We want more files, we want more data, we want availability in all the three forms of it, which is load balancing of metadata traffic, so that we never get into a point where a single bad job saturate the whole name node. We want same data streaming speed to data nodes, and we don't want a single point of failure. Also, we want to keep this massive amount of servers from management point of view as a single cluster. So there are some numbers comparing current HDFS with federated projection and projection for Giraffa. Basically, it's 1 exabyte. We want Giraffa support 1 exabyte of total data, 100 billion objects, and 1 million concurrent clients. So people asking question, why HBase and HDFS? Well, first of all, building a new file system from scratch is a hard work and can take at least a couple years. So HDFS is reliable block storage. We know that already, and provides efficient data streaming and data node recovery. If they fail, it's not a big deal. HBase on the other hand is a distributed cache, so it will work the same as name node that serve metadata from memory. It has dynamic partitioning, and it has automatic metadata recovery. Also, we want we think that HDFS and HBase are sort of the same breed, so you don't need a different type of storage. For example, if you use MySQL, that's a different type of storage. Here we'll have everything under one roof, and will not need to maintain two different code bases or softwares. So some people ask, why don't you just use HBase and store everything in it? Yeah, it's possible, but it defeats one of the main principles that data streaming should be separated from metadata operations. We can store small files as rows. That's not a problem, but the row is limited in theory by the size of the region served. So really big files you have to split. Technically, you can split anything. Log files splitting by events, video files can be split by frames, even random bits can be split into fixed size chunks and keyed by offset. But that's a different abstraction. You will have to convert your data. We want to keep video files as is in HDFS. So if I'm not targeting 1 exabyte, just got 1 petabyte, do I still need Giraffa? Yes, you do, because of the availability requirements that we are targeting. And because small files, you can store lots of small files. We know that in clusters, in current clusters, the block to file ratio is shrinking. When you have a brand new cluster, it's around 2. When the cluster gets to 80–90% full, you will see that it will be 1.2 or even 1. So there are 3 building blocks for Giraffa. It's a namespace table, single table that we call namespace. It's keyed by file IDs, and we'll talk about later in more detail. It has attributes, it stores attributes of the file like name, replication, block size. It stores list of blocks, and it stores block locations for each block. Giraffa client, the same way, provides connection between metadata and data itself. So it will work exactly as the HDFS client. And block manager is the new layer that sits between HBase and data nodes and maintains the flat namespace of blocks. First of all, it provides block allocation, replication, removal, data node management, and storage for the HBase table itself. So this is the picture I drew. Does it look good? Oh, okay. So there is an application which talks to the Giraffa client, and there is a new communication layer which is namespace agent, which talks to the HBase instead of the name node itself. HBase stores all those rows. Every row represents a file, and it talks to the block manager via block manager agent. That's also a new communication component, which and then block management, as I said before, is the manager for blocks themselves and data nodes. So everything is from HDFS or HBase, except for the two communication layers that I mentioned before. So row keys identify files and directories. And in Giraffa, we want to experiment with different key definitions in order to provide locality. We'll have a couple of slides after later. The definition of the key should be determined at format time, and the default current implementation is the full path definition. So these are the columns, and they contain file attributes and blocks locations. And for directories, we, instead of blocks and block locations, we store the directory table, which maps basically the entries of the directory to the row keys that correspond to those entries in the real table. So Giraffa client. Giraffa client is an implementation of file system. As usually in HDFS, you need to provide a new URI. For Giraffa, it's GRFA, and provide the implementation of class, which is Giraffa file system class. Giraffa client extends DFS client. By that, we sort of inherit all the logic from HDFS that communicates between metadata, between name node and data nodes. We only need to substitute the RPC to the name node with this communication component, which is called namespace agent. The rest is taken directly from HDFS. Block management. I already talked about several here things. Block manager is also a distributed component. Block manager server is paired with the region server, runs on the same node. If the region server fails, then region blocks will be rescheduled on different nodes. Same with block manager servers. Block manager server is not a new component right now. We'll reuse namespace, the name node as is, and try to sort of adapt it for the new purpose. So 3 problems that arise with respect to Giraffa are bootstrapping, because HBase stores data in HDFS file. Namespace partition, we want to retain locality of files. And atomic rename. So some answers to these questions will be algorithmics, but some philosophical. So that's why the angles is here, right? So bootstrapping, I wanted to put some words here, but then I thought that I'll just put a picture, and it might tell more than many words. So basically, on the block manager server, we have 2 types of metadata information. First is the HBase volume. I call it HBase volume. This is a representation of the table itself layout in the block manager space. So this is a typical file system, but it's very small, and it's changing very rarely because the regions are changing when you create new regions or contract, and because it's small rows, then it's not very rarely changed. Files in the region are blocks in the same file system, so they go into the second part of the block management. Better? So the block volume on the block manager server consists of blocks. And so we think of blocks as a single block files, which each file has the name of the block ID that it contains. So the block ID that files has and the name of the file coincide. That way we sort of have one-to-one correspond between files and blocks. And this is a flat namespace. We don't need to think about it or replicate it anywhere because all this information is already stored in the HBase table. And when the server starts, it can get this information from the table itself and populate this namespace from HBase table. And the block locations, of course, will come from data nodes. So the only thing we need to take care of is that small HBase volume there. And it's really small, but we need to take care of it. So what we propose is to put the image, with the FS image, the file that stores a checkpoint of the namespace into the file system itself, and store it as a special file or a special set of blocks. On startup, the block manager server reads that. It reads the journal, which is another special file or a special block, reads that too, and populates this small namespace internally. And that gets it ready for, that's a solution for the bootstrapping problem. So, locality of reference, it's a known notion in file systems. We want to keep directory entries close in the row because we're flattening the namespace tree into linear structure, and that's why we want in this linear structure be also close. There are several ways to partition it. The naive partition is anti-local partitioning because files of the same directory go into completely different places. So this is hashing. The color is the value of the hash. So this is more traditional partitioning used in SAF. The whole subtrees are partitioned into sort of regions. And the third way is to partition based on the fixed height. Here is the height. The depth is 1. So the whole directory, the whole set of entries of the same directory go into one single partition, and they always kept close to each other. So. Atomic rename is another problem that we want to target. There will be no atomic move in POSIX sense, so we're not moving from one directory to another. But what we can provide and will provide is in-place atomic rename. And turned out that for many applications, that's enough functionality because you can use some algorithms that first of all do renames, move files from one directory to a temporary directory, then remove the old file by and then recovering if it fails on the way. That can be done very, very simply. If it is necessary to provide the full-fledged functionality of atomic renames, which is moving, we can do it as a separate function, which will use Paxos or other simplified synchronization algorithm. So a little bit of history. The idea was born in 2008 when I was looking at all those working on HDFS, first of all, and studying other file systems. A partitioning of the namespace, the 4 types of partitioning were also born at that time. The study on scalability, when I realized that the scalability must be limited at some point, I put some effort into understanding how much scalability we can get, and there was some optimization on the name node made at that time that lets scale the file system larger. We had some designing meetings and discussions with Michael Stack, which ended up as a presentation on HDFS contributor meetings. In 2011, Plamen implemented the POC of Giraffa. It was pretty good. We rewrote the code base, right, and put it in Apache extras. So this is the link. You can click on the link or copy. So the status of the project, design stage, that's one of the design pictures we drew with Stack at the point. And one node cluster running, live demo is provided by Plamen soon. So thank you and happy giraffing. We're looking for committers, of course. It's very easy to get a committership in giraffing. Questions? There's mic.
Please use the mic. Yeah.
So there's been some, obviously, work on Federation, and you touched on that a little bit. But it seems like Federation does a lot of the scalability that you seek, except for one thing, which is auto-balancing. And of course, the crux of that is atomic rename. So I have to wonder if there's another way to go about this from that angle. I mean, do you think that's viable, or is there a fundamental obstacle there?
No, federation is a step, and federation is done in the way I participated in discussion and design of federation. It's done in the way that the block management part can be used, not directly right now, but can be transformed into something that can be applicable in Giraffa. The data node reporting to different name nodes can be used in Giraffa, and when we port it into 23, it's going to be easier to do many things. So it's an evolution. Mm-hmm. I see that as a next evolution.
Hi. So is there any work related to block access tokens for security reasons? I believe like all the metadata operations for the namespace would be done on the client-side libraries with that. So is there any work or roadmap for that?
Yes, so very good question. So what we want to do right now, we did implement the logic, the namespace agent logic on the client, but we want to move it into the server using endpoint coprocessors. And then you can specify the ordering of coprocessing in HBase, and then security coprocessor will run before that, and will provide full security for that system. Okay. Make sense?
So you're going to use the HBase security model on top of, for implementing the HDFS security model, right?
Right. So both models, HBase and HDFS, will work fine because we'll hide all the logic under behind the HBase security. So okay. We'll first hit HBase security, then we'll run Giraffa code.
Okay. Okay. Thank you.
I have a question on how the HBase compassion region server performance would affect Giraffe.
You want to take it? Yeah, sure. So it's a very interesting question, and I guess we'll have to see that in practice, because it could affect. I totally agree. On the one hand, on the other hand, the direct access is going to memory, is hitting memory, so it might not be such a big effect for Giraffa.
In the interest of full disclosure, despite that we have the same T-shirt, I have no idea about where the project is. And you said that you are interested in committers, how one can find the project on the web and how one can join.
So there's a link in the presentation. You can click on the link, and there is a project there. And so we're two committers there. Send me an email. And if you want, there is an issue link there. So I filed several issues. So you can comment on the issues. I'll notice that.
Sorry, I must have missed it then. So thank you.
We're out of time.
So waiting, Plamen is waiting for, oh, okay, go ahead.
Okay.
So doing the federation, the way you're doing, everything is about read and Hadoop, right? How fast you're going to read. You have done some benchmarking on any value. You're going to have a plugin Giraffa?
No, we didn't do much of benchmarking. We can do it on a single node at this point. That I don't see much value of that.
But do you see some speed effects on distributing the name node? Because I doubt distributing.
Yeah, no, again, like I don't know too much, but yeah, we would probably see kind of a loss in performance, but at, like to what end we would get basically a distributed name node. That's what we're looking at.
Probably there will be loss of performance at times when regions migrate, but other than that, I don't see how the performance will be affected.
Yeah, it should be little overhead.
Second question, modify support. Is this something you plan or append?
What?
Oh, append. Are we going to
append.
support-
Yes, because because Giraffa client is exactly HDFS client. Append basically will follow the same algorithm that was implemented there, and we'll just need to provide the metadata operations that support those append algorithms. Yes, we definitely will. Thank you. All right, thank you.
Yeah.